अच्छा है, मेरा तो ब्लॉक ना 4 बजे पहले तो 100 कॉल दर्शन कर ये हाँ बता भी देना।
Okay, so in the last class we started looking at concept of linearization. We said in this particular course we will be mostly concentrating on linear equations instead of looking at non-linear equations. So whenever we will get the non-linear equations, we are going to linearize them by using Taylor series expansion. Please come in the front. So typically the linearization is performed by using the Taylor series expansion. The example is given here. If we are having a differential equation dx by dt equals to f of x, and let's say this f of x is a non-linear function. So if f of x is a non-linear function, then we are going to linearize by using Taylor series expansion, which is given here. So in a Taylor series expansion, we are going to omit all higher order terms, and we are going to retain only the first order term. And with this first order term, we will have a linearized equation. So typically what we do, whenever we are having a non-linear function, we are only finding a tangent to this non-linear function, isn't it? So you can see that this first term which we have retained here, that is nothing but the equation of this tangent. Is it clear to everyone? Then we said that usually we have multiple differential equations, multiple non-linear functions are there, In such cases, we have to linearize all non-linear functions with respect to the given variable. One example is given here. So you can see that we have two equations, dx1 by dt and dx2 by dt, and both these equations are function of x1 and x2, isn't it? So f1 is also a function of x1 x2, f2 is also a function of x1 x2. So we can use the Taylor series expansion to linearize this f1 and f2 both, isn't it? So you can see that f1 is linearized in this manner. So f1 x1 x2 is given as f1 at x1 0 x2 0 plus df1 by dx1, and this derivative is calculated at known values x1 0 and x2 0 multiplied by x1 minus x1 0 plus dou f1 by dou x2. Again this derivative is calculated at x1 0 and x2 0 multiplied by x2 minus x2 0. Okay. So if we are having the equation like this, then we can again linearize and we can use the linearized equation, isn't it? So if we use the linearized equation instead of a non-linear equation in a given differential equation, then the solution becomes easy, isn't it? It's not that we will not be able to handle non-linear differential equations. We can handle that, but for a time being, we are only concentrating on linear process terms. Okay. So this is the typical example. Remember, we have started looking at non-isothermal CSTR, isn't it? Where the input is Ca. Maybe I can go. This is the example, non-isothermal CSTR. So you can see that the input is CAI, FI, TI, output is CA, F and T. Our objective is to maintain the temperature inside the reactor. Another objective is to maintain the concentration of effluent coming out from the reactor, isn't it? So CA and T we wanted to maintain inside, isn't it? Correct. Again, just for a simplicity, if we assume that the inlet flow rate is not changing, so if this inlet flow rate Fi and the outlet flow rate F both are same, in that case we can say that the height of the liquid present in the tank is not going to change, isn't it? So the first differential equation, remember in this case we are going to get three differential equations. In fact, four differential equations we are going to get. One for height, then concentration, isn't it? And then temperature. Three differential equations we are expected to get, isn't it? But if we are assuming that this Fi is not changing, Fi is exactly same as F, in that case this first differential equation will not be required, isn't it? And the other two differential equations which we will be looking at will be this, isn't it? The first one will be V dCA by dt is given as Fi CAI minus CA minus V into K naught e raised to the power minus E by RT CA. And the second equation will be this. V dt by dt is given as Fi in the bracket Ti minus P plus minus delta HR V K naught e raised to the power minus E by RT CA divided by rho Cp minus UAT T minus Tc by rho Cp. Now if you look at this equation and the other equation we have obtained, isn't it? So this equation as well as the earlier equation, which is this equation, in both these equations you can see that this term is non-linear term. This is a non-linear term, isn't it? So clearly the model equations which we have obtained are non-linear in nature. We wanted to get the model equations in a linearized form. So what we have to do? We have to linearize this non-linear term. Okay. So let me go back again to the same slide. So these are the two equations we are talking about. You can see that this first term here is the second term here, and the same term which is there in the another equation. Both are non-linear, and these non-linear terms we have to linearize by using Taylor series expansion. Now this particular term, if you look at, ये sound कर रहा है, यहाँ से बंद कर दो तो कोई नहीं, ऐसे करने ये भी बता दूँ, बार बार नहीं बनाना, निकालिए, ठीक, ओके. Now this particular term, if you can see that this particular term has two variables, T and CA, both are variables, isn't it, in this case? So we have to use multivariable Taylor series expansion, which we have seen in the last slide, isn't it? So you can see in the last slide, we have seen this multivariable Taylor series expansion. Same multivariable Taylor series expansion we have to use in this case for this non-linear term. So e raised to the power minus E by RT CA we can linearize as shown here. So you can see that this term we have to first calculate as CA0 and T0, isn't it? So that is what is given here. E raised to the power minus E by RT0 CA0 plus derivative of this particular term into T minus C0 and derivative of this particular term with respect to another variable into CA minus C0. That is what we have written here. T dou f1 by dou x1, isn't it? And then x4 minus x1 0, and the second term is dou f1 by dou x2. Correct? So same thing we have done here. So derivative of this particular term with respect to t is given by what? E by RT naught will come out into e raised to the power minus E by RT naught. Remember this derivative we have to calculate at the known values of the variable, which is T naught and CA naught, isn't it? So this derivative we have calculated at T naught and CA naught, so that becomes E by RT naught square e raised to the power minus E by RT naught into CA naught. Okay. And outside will be T minus T naught. Similarly, again we have to get the derivative of this particular term with respect to CA, isn't it? So derivative of this particular term with respect to CA, what we are going to get? This e raised to the power minus E by RT will remain as it is because there is no CA term, isn't it? That will come out. So e raised to the power minus E by RT naught, because we are finding out the derivative at the known values T naught and C naught, so that will become e raised to the power minus E by RT naught into derivative of this term is just 1 and multiplied by CA minus CA. Correct? Now if you look at this equation, in this particular equation you can see that even though this equation looks non-linear, but it is not non-linear, it is linear. Why? Because this term we are calculating at known values of CA0 and T0. So we will get a value here. you will get some value here. Similarly, you will get some fixed value here, some fixed value here, isn't it? So some fixed value multiplied by t minus t naught plus some another value multiplied by c and c naught. So you can see that this equation looks non-linear, but it is not non-linear, it is linear. Clear? So once we have obtained the expansion of this particular linearization of this particular term, that we can again back substitute in the original equation. So with that, what we are going to get is dCA by dt comes out to be 1 by tau Ci minus k naught. That k naught will remain as it is, and this entire expansion term we have taken in the bracket. Same thing we have done in the second equation as well. So here dt by dt is given as 1 by tau Ti minus t plus jk naught into this entire term. Remember this jk naught is, and this entire term is replaced by the linearized. So this linearized term again we have put in place of this, isn't it? That becomes this, and the last term remains as it is. So last term is ua by rho cpv t minus cc. Correct. So now both these equations are linear differential equations, isn't it? Earlier they were non-linear, but now after linearization of this non-linear term, we have obtained both these equations which are linearized. Okay. Remember I said that in this particular course, whenever we are deriving any model equation, ultimately we make all these model equations in a deviation form. Okay. So we are also going to make these two equations in deviation form. These two equations are now representing the dynamic picture. But if I subtract the equation corresponding to steady state from this, then I am going to get the equation in a deviation form. Correct? So at steady state, what is going to happen to this equation, these two equations? So at steady state, we will have the left hand side 0, isn't it? Right hand side, if I go back again, these are the equation. So this left hand side will become 0 because at steady state, concentration and temperature is not varying with respect to time. So left hand side becomes 0. This CAI will become CAIS, steady state value of the input concentration. And this Ca will become CAS, steady state value of the outlet concentration. This K naught into e raised to the power minus e by RT naught Ca naught. Now this Ca naught is what? The steady state value. Ca naught is the steady state value. Initial value is the steady state value. This will remain as it is. This e by RT naught square into e raised to the power minus e by RT naught. This is again a steady state value Ca naught. It will remain as it is. But what will happen to this? T minus T naught. So T will become a steady state value which is nothing but T naught. So T naught minus T naught 0. So this term will go away. Similarly, this last term will also go away. Why? Because this Ca will become Ca naught. Isn't it? Same thing happens here. So this term will go away and this term will go up. Isn't it? So with that, you can see that at steady state, the remaining terms we will be having will be this. So 0 equals to 1 by tau Ci naught minus Ca naught minus k naught into e raised to the power minus e by RT naught Ca naught. And similarly, in the second equation, the left hand side is 0 equals to 1 by tau Ti naught minus C naught plus jk naught into e raised to the power minus e by RT naught Ca naught and minus u by rho cpv T naught minus Tc naught. So you can see that these two terms will vanish here, and the other remaining term we will have. This Ca will become Ci will become Ca naught. This will become Ca naught. This will become Ti naught, and this will become T naught. That's it. So that is what I have written. Okay. So once we have obtained these two equations at steady state, I can subtract these two equations from the original equation. The original equations are isn't it? Original equations are these two, isn't it? If I subtract, what I want to get? I want to get dCA by dt, and dt by dt because left hand side is 0, doesn't matter, isn't it? I could have written this dCA minus C naught by dt. In that case also it doesn't matter because derivative of this steady state value is 0, isn't it? So left hand side will be dCA by dt and dt by dt, and right hand side you can see that the corresponding steady state values are subtracted from the respective variables. Okay, so you can see that Ci minus Ca naught, Ci naught, and this becomes Ca minus Ca naught. Similarly, this first term will get cancelled out. So this first term will get cancelled out because this is the term which is there in the steady state equation. So this will get cancelled out, and the remaining term will be as it is. So the remaining terms are as it is, you can see. Okay. Yes, no. So once we have obtained these two equations in a deviation form, I can represent these two equations in a deviation form as shown here. So we can represent them as dCA dash by dt, which is equals to 1 by tau Ca I dash minus Ca dash plus minus k naught in the bracket e by rt naught square, e raised to the power minus e by rt naught Ca naught, and this t minus t naught is represented by t dash. Similarly, the Ca minus Ca naught is represented by Ca dash. Okay, same thing is done in the second equation. So you can see in the second equation also we are having t dash and Ca dash, correct? And the last term, which is this, so this becomes minus ua by rho cpv, t minus t naught is t dash, and minus this tc minus tc naught is tc dash.
Here T naught is the initial temperature of the...
So we are assuming that the system is at steady state at time t equals to 0. So these are the steady state values.
Okay. But I wonder also like when you are considering steady state, but there can be what to say disturbances in the input field, right? Input field.
So that is what we are saying. Initially the system is at steady state, means whatever the value we are having with respect to that,
we are setting that to steady state.
That we are calling it as a steady state. Okay. There could be another steady state once the disturbance is already there in the system and you have achieved another steady state. Remember we get another steady state?
Yes.
But here we are interested in what? We are interested in finding how much my control variables are varying with respect to my initial steady state. So you can see that all these variables which are denoted by dash, Ca dash, T dash, Tc dash, all these variables are actually deviation variables. So these are nothing but how much these variables are varying with respect to their steady state values at t equals to 0, time t equals to 0. Okay? Clear?
What is J in the temperature equation?
So we have defined the J here, you can see, I can go back. Remember we have delta minus delta HR by rho Cp. So that term we have defined as J. I will go back just to give you more clarity. See, minus delta HR V by rho Cp, this entire term is denoted by J. In fact, this V also comes in here. This entire term is defined as J. Okay? Okay, now coming back to the next topic. Remember what we have done? We started this course with the, we have discussed in the first class why process control is required. Then we have slowly, diverted our attention to the modeling part. We said that for process control, unless you know your system, you will not be able to do anything. So for knowing the system, you need to have model, isn't it? Then after that we said, okay, we are having a model. isn't it? We know what to do in the system, isn't it? Then in order to control the system, we have to monitor the system. So we have seen how we can measure different variables. Then we have seen how these measurement values we can use intelligently to add external interventions, isn't it? So there comes proportional controller, PI controller and PID controller, isn't it? Then we said, okay, this is all right, isn't it? This is very simple for the toy problem which we are looking at. But when the problem is more complex, in that case we will have large number of differential equations which we have to solve together, isn't it? In such cases, finding the degree of freedom becomes more important, primarily because how many control loops required, that is actually equal to the degree of freedom, isn't it? And if you miss this particular fact, then you end up with getting erroneous results. Because if your number of equation and number of variables are not same, you will get infinite solution, isn't it? Correct. So finding the degree of freedom is extremely important, isn't it? After that we said, okay, story is going very well, but then we said that the problem will have non-linear equations. We don't want to deal with non-linear equations right now. There is a separate branch of process control which deals with non-linear equations, which is called as non-linear process control. We don't want to go there. We wanted to keep our focus only on the linear equations, isn't it? The reason behind that is, if you are having linear differential equations, we can solve these linear differential equations easily, isn't it? Correct. So we said we will linearize all these model equations, those are non-linear. Correct. Now we are again going one more step ahead. We are saying that solving these differential equations is difficult, isn't it? So I don't want to solve them directly in T domain. But if I apply a Laplace transform makes or converts the differential equations into algebraic equations. So linear differential equations will be converted to linear equations, isn't it? So if you are having simultaneous differential equations, which is the usual case, if you apply the Laplace transform, you will get the simultaneous linear equations, and simultaneous linear equations you can solve easily by using concept of matrices, etc. It is easy to solve, isn't it? So now we will be focusing on Laplace transform. Everybody is able to understand why Laplace transform? Laplace transform because Laplace transform is going to convert your differential equations into algebraic equations, and handling algebraic equations is much more easier compared to handling the original differential equations. Is it clear? Okay. Now let's look at the definition of Laplace transform. Anyway, you all might be knowing this, but just for a sake of continuity, we will be doing it quickly, isn't it? So Laplace transform definition is given here. Laplace transform of any function f of t, we represent that as f of s, and you can see that this function f here and the function f here, they are not same, they are different. And in order to distinguish that, a bar is kept here. So you can see that this f here and the f bar here, they are not same, they are different. They are different. Okay. But you will see that in this code probably later I am going to omit that bar, because every time putting a bar it is too much work for me to make the slides. In fact, all these slides I have made myself. I have not copied it from the book. You will see all the figures are newly made. These are not copied from the book. Okay. So it becomes difficult to make the bar every time. So you will see that after some time I might have omitted this bar. But don't get confused. If you are performing the Laplace transform of function f, the equivalent function which you are representing in a S domain is not same. It is different. Okay. So Laplace transform of function f of t is represented as f of s, and the definition of Laplace transform is integral between 0 to infinity f of t e raised to the power minus st dt. This is the standard definition of Laplace transform. Okay. Now what is S here? S is a variable in a complex plane. So what we are converting? We are actually mapping the problem which is initially at T domain into a S domain. Okay, alright. Where the S is given as A plus J beta. Here A is the real part of the variable S and B is the imaginary part of the variable S. Okay. Now let's look at some of the properties of the Laplace transform. I will quickly go through this. So if we take the Laplace transform of function like this, let's say two functions are added, a1 f1t plus a2 f2t, and we wanted to take the Laplace transform of that. You can see that we can take the Laplace transform of individual functions and we can add. So same thing is shown here. So you can take a1 common and f1t Laplace transform of f1t will become f1s plus a2 into f2s. That is what we are going to get, and that we have proven here. So Laplace transform of a1 f1t plus a2 f2t, we can use the standard definition of the Laplace transform, which is integral between 0 to infinity. This entire function is multiplied by e raised to power minus st and dt, and this entire term we are integrating between 0 to infinity. We can separate these two terms easily. So a1 integral between 0 to infinity f1t e raised to power minus st dt plus a2, which is constant, again we have taken it out from the integral sign, integral 0 to infinity f2t e raised to power minus st dt. So now you can represent this particular term as f1s, and the second term you can represent it as f2s. Okay, isn't it clear?
Yes, sir.
Good. I want many people to say yes like this. Who said yes? Good. Okay, so this is very simple. Now let's make our life slightly more complicated. Have you done Laplace transform by the way?
Yes.
All of you? Is there anyone not done Laplace transform? You have done in your JEE, is it?
No. MPL 101.
So then I am not sure whether you have done or not.
No, sir.
MPL 101.
But if it is in JEE, then probably I can safely assume that you have done. Alright, so I take my words back. Let me assume that you all have. Okay. Now let's look at the another function f of t is given as e raised to power minus at. E raised to the power minus at, where t is greater than 0. Okay. We wanted to find out the Laplace transform of that. So L of e raised to power minus at, we can use the standard definition. This is integral 0 to infinity e raised to power minus at multiplied by e raised to power minus st dt. Isn't it? We can simplify this. So it becomes 0 to infinity e raised to power minus s plus at dt. Isn't it? And integral of this particular term will be what? S plus a term will come in the denominator. So minus 1 by s plus a into e raised to power minus s plus a into t, and this integral is varying between 0 to infinity. So that is what is taken the limit here. I can simplify this entire term. What I want to get is 1 upon s plus a. 1 upon s plus a. Okay. So we are deriving these equations here, but you will see later that we are going to use the Laplace transform of these commonly used functions directly. We are not going to derive it again and again. Okay. So whenever I am having a exponential function like this, e raised to power minus at, its Laplace transform is 1 upon s plus a. Let's look at the another function, Laplace transform of at. It's a ramp function, isn't it? Continuously the function is increasing with respect to time, isn't it? If I am having a function at, what it means? Where t is the time. So the function is increasing continuously with respect to time as time increases. Now again use the same definition of Laplace transform, 0 to infinity at e raised to power minus st dt. We can use this rule, integration by part, isn't it? So we wanted to find out the integral integral of this entire term, isn't it? We can. So see, this e raised to power minus st, this particular term we can take as v. So what will be dv? Minus s into e raised to power minus st, isn't it? So from that, if we rearrange, what will be uv? uv will be minus at by s e raised to power minus st. That will be the first term. And integral value will be 0 to infinity. Is it clear to everyone? What I have done here? I have taken this particular term e raised to power minus st dt as dv. Isn't it? So what will be v? So that's what this term will be v. Isn't it? So u will remain as it is, so at will remain as it is, and dv will be e raised to power minus st by. Correct? Is it clear? And the next term will be minus of v du. So once we have obtained this entire term is v. Remember, e raised to minus e raised to the power st by s. This is the term v. Isn't it? And that minus sign will get cancelled out with this minus sign, so that becomes plus here. Isn't it? And what will be the derivative of u? Remember here du is there, and u is this term at. What is the derivative of at? Just a. So that becomes integral a by s e raised to the power minus st dt, integral varying between 0 to infinity. Okay. Now we can solve both this term. This term you can solve easily, isn't it? If you put this t equals to infinity, then this e raised to power minus st becomes 0. And when you are putting t equals to 0, this first term becomes 0. So in both the limits, this entire term becomes 0. So that is why we have written minus 0 plus 0. And what will be the integral of this term? A by s will come out, and integral of e raised to power minus st dt, that becomes e raised to the power minus st divided by minus s. Isn't it? So that is what we have obtained. Again we can put the limit 0 to infinity. Isn't it? So what will happen to this particular term when t is infinity? It is 0. Minus, when you put t equals to 0, that becomes plus here. Isn't it? That becomes a by s here. Is it clear? Because 1 by s is outside here. Is it clear to everyone how it is done?
Yes.
Alright. Now let's make our life slightly more complicated. Take another function which is sin omega t. Now sin omega t, we can represent sin omega t in terms of exponential terms. Isn't it? We can represent this sin omega t as e raised to the power j omega t minus e raised to the power minus j omega t divided by 2 iota. Isn't it?
Yes,
Now these are the exponential function. We have already seen how we can find out the Laplace transform of exponential function. Use the same property, and with that we can get. So you can see that e raised to power minus st is there. That if you add in both these terms, what you are going to get is 1 by 2 iota out e raised to the power minus s minus j omega t minus e raised to the power minus s plus j omega t and outside dt. So these two terms are the exponential term. What will be the Laplace transform of this first term? This term as it is divided by s minus j omega.
1 by s.
Isn't it? So minus sign will get cancelled out, so that becomes s minus j omega. Correct? And the second term, again s plus j omega you are going to get here. And if you rearrange everything, limit is between 0 to infinity, what you are going to get is 1 by 2 iota 1 upon s minus j omega minus 1 upon s plus j omega, because this first term, when you are taking the limit infinity, that becomes 0. Isn't it? But when you are taking the limit 0 to minus sign, this will get cancelled out, this will become minus here. Isn't it? So ultimately the remaining terms will be what? 1 upon s minus j omega minus 1 upon s plus j omega and 1 by 2 iota outside. So this entire term, if I rearrange, we get omega divided by s square plus omega square. A similar analysis you can do for another term which is cos omega t. So cos omega t you can again represent in terms of this exponential terms, like cos omega t is given as e raised to the power j omega t plus e raised to the power minus j omega t divided by 2. Isn't it? You can take this expansion here and use the definition of Laplace transform, solve. Ultimately what you are going to get is s divided by s square plus omega. Clear? Now let's look at slightly more interesting function. We are interested in looking at step function. Why we are looking at the Laplace transform of all these sinusoidal function, step function? We will also look at impulse function, isn't it? Why we are looking at it? Because these are the functions we are going to use directly later in process control. Okay, so we are not going to derive their Laplace transform later. We are going to use their Laplace transform directly. So let's look at the step function. So step function is what? At time t equals to 0, the function is changing from its value 0 to a new value. Let's say the new value is a. So initially the function f of t is 0. For all the times before t equals to 0, the value of the function f of t is 0. But at exactly time t equals to 0, my function is changing from 0 to a. Isn't it? And it is remaining there. The function is represented here. You can see initially it is 0, and then at time t equals to 0, its value becomes a, and it remains a after that. It's a step function. Okay. Now again we can apply the definition of Laplace transform. So definition of Laplace transform of f of t will be given by integral 0 to infinity a into e raised to the power minus st dt. A is a constant term that will come out, and integration of e raised to power minus st dt will be e raised to the power minus st divided by minus s. Isn't it? So we will have minus a by s e raised to the power minus st and limit 0 to infinity. If you put everything here, you will get a by s. So Laplace transform of step function with a magnitude a is nothing but a by s. Let's say if you give a step input of magnitude 1, what will be the Laplace transform? It will be 1 by s. Okay. Now this is the translated function. Remember I said translated function we are going to look at later. Whenever I am measuring something, I am not going to measure the value exactly with respect to that time step, isn't it? Because every measurement unit is going to take some time. Or even if I am adding any external intervention in the reactor, it will not get implemented immediately, isn't it? That is what we have seen. A typical example is pressure example in reaction engineering, isn't it? If you add the dye inside the flow reactor, you will be able to see the dye in the outlet only after some time. The minimum time required to visualize the dye will be the residence time, isn't it? Correct. So you can see that in all process application, whatever you do, either you do the measurement or either you do the external intervention, that is going to impact the system only after some time. It is not going to happen immediately. So there is a delay or there is a dead time associated with each and every process which we are looking at, isn't it? A similar thing is represented here. You can see that output here, output f will be function of the input, isn't it? But it will be delayed by a time td, and that function we are calling it as a translated function. So translated function is represented as ft minus td. I will go back again just to give you a more perspective here, because this is an important point. In fact, I said this earlier also. One of the most detrimental factors for the stability of the process system is dead time. Okay. So dead time we have done somewhere, if I am not wrong. See, this is what we have described earlier, dead time or a time delay, isn't it? So out t out is a function of t in, but it will be delayed by a time td. It will be delayed by a time td, isn't it? So if I change the inlet temperature of the plug flow reactor, the change will, you will be able to see that change in the system only after the wait time td, isn't it? Correct? And that wait time you can obtain as a residence time, which is nothing but volume of 5 divided by volume of T in this case. Correct? So how many of you have taken these slides from the school? These slides are already kept in the school. You can get the Xerox copy. Okay. Okay, so this is the translated function. Now again let's apply the definition of Laplace transform to the translated function. Okay, so what will be the Laplace transform of this particular function? L of f of t minus td, isn't it? So f of t minus td into e raised to the power minus st dt, isn't it? I can subtract e raised to the power minus. Here I can add, and that I can put it outside. E raised to the power minus std I can put it outside, and this term is added here. You can see. So it will get cancelled out, isn't it? So what we are getting is e raised to the power minus std out, integral 0 to infinity. Remember there is no t here. Td is a dead time. It's not a time. So it's a different variable. So e raised to the power minus std we have taken out from the integral side. And inside the integral side you will have f of t minus td e raised to the power minus st minus td into dt minus td. And now we can replace t minus td, we can represent as tau. So if we represent t minus td as tau, this entire function will become what? This entire function will become e raised to the power minus std f of tau e raised to the power minus s tau into d tau, and also the limits are going to change. So this upper limit which is infinite, that will remain as it is, but the lower limit, instead of 0 we will have a lower limit which is minus td, isn't it? You can have that directly here. If you put t equals to here, what you get? Tau is minus td, isn't it? So your tau is going to vary between minus td to infinity. Okay. Now this particular function is we are familiar with. Remember this particular function looks very similar to the definition of Laplace transform. The only difference here is the limit is starting from minus td to infinity. I wanted this limit to be starting from 0 to infinity, isn't it? Then and then only it will become the definition of Laplace transform. And that is easy in this case. You can see what is f of t. F of t is a variable. Typically we take all these variables in a deviation form. So all these deviation variables before time t equals to 0, what is their value? 0. So integral between minus td to 0 for f of t dt is 0 actually. So there is no problem if I replace this minus td to 0, because the integral between minus td to 0 for this entire function is actually 0. So I can replace this lower limit here by 0. Okay. So with that my equation will become e raised to power minus std integral varying between 0 to infinity f of tau e raised to the power minus s tau d tau, and this entire integral we can represent as f of s. So now this final equation is interesting. This final equation is interesting because whenever a dead time associated with the system, I just have to multiply e raised to the power minus std term and calculate the Laplace transform of a function without translation. Remember, this is a translated function. This function is giving you the output after time td. Now with this, what I am doing, I am actually calculating the Laplace transform of function f of t isn't it? And multiplying e raised to the power minus std. That's it. So whenever there is a date time associated with the system, you will see that this additional term e raised to the power minus std comes into the picture. And this is a very interesting term. Why? Because you will see in the process control that this term is actually making your life difficult in process control. This particular term is responsible for unstable control system. Okay. Alright? Okay. So the same example, T out is represented as Tin minus T Td, T minus Td. That can be represented as T out S is given as e raised to the power minus std into T in. And I have represented all these functions by bar. Isn't it? So that means this function is not same as this function. They are different. Okay, just to distinguish them, I have put a bar. Now again, so see, so far we have seen these step functions. Let's look at the pulse function. So pulse function is what? You can see that you are having a signal 0 before time t equals to 0, and time exactly t equals to 0. I am giving a step input of magnitude 1 by a, and I am continuing with this magnitude for a time duration of a. So you can see that difference between this time and this time is a. And at time t equals to a, I am again giving a negative step and making the signal 0. So you can see that the signal is at 1 by a only during this particular time period, and the time period is a. Isn't it? So this particular function we are calling it as a pulse function. How we can define this pulse function? Mathematically, delta a t is represented as its value is 0 when time is less than 0. Its value is 1 by a between time 0 to a, and it is again 0 when time is greater than a. Now this particular function I can represent combination of two step functions. Remember I said this is one step function and then there is a negative step function here. So if I subtract two step functions from each other at different time, I will get actually the pulse function, isn't it? So in this case, if I have to draw it, actually if I have to draw it, it is something like this. So I am having a step function, one step function like this, isn't it? Which is continuing, and then there is another step function which is continuing, and both these step functions I am subtracting. So if I subtract both these step functions, actually the resultant function which I am getting is something like this. This is what is happening. Okay, you can see that. So the same thing is represented in this slide here. So this is the one step function I have represented. You can see that at time less than 0 the value is 0, and time greater than 0 its value is 1 by a. Another step function I have represented as its value is 0 when time is less than a, less than equal to a. So remember, this time is 0. This time is 0, and this time is t equals to a, isn't it? So you can see that this is f2t, this is f1t. So now these two step functions, the another step function, you can see that its value is 0 till time equals to a, and when time is equal to a, at that time its value becomes 1 by a, and it continues with the value of 1 by a. Okay. Now this is an interesting function. Why it is interesting function? Because it is exactly same as f1t. The only difference is it is translated by a time a. Same thing is happening exactly as function 1, but it is happening after time a. It's a translated function. So I can represent this particular function as f1t minus a, isn't it? And then I can subtract both this f1t and f1t minus a, that gives me this delta function, first function, isn't it? So f1t minus a, I can apply the definition of Laplace transform. With the definition of Laplace transform, remember this is Laplace transform of f1t, and what will be the Laplace transform of this? This is a translated function, so e raised to the power minus st will come out. In this case, how much is the time delay here? A. So e raised to the power minus sa will come out into Laplace transform of f1t. Is that I can take Laplace transform of f1t common, it becomes 1 minus e raised to the power minus sa, and Laplace transform of step function is what? Laplace transform of step function, whatever the magnitude is there divided by s. In this case the magnitude is 1 by a, so the Laplace transform will be 1 by as. So ultimately the Laplace transform of this function is 1 minus e raised to the power minus sa divided by s. Okay, so we will continue from this point in the next class. Alright.
Gracias.